every flight you've ever taken was guided by an invisible hand. Inside the cockpit, a screen shows a perfect route through the empty sky. But that route isn't magic. It comes from satellites orbiting 20,000 kilometers above Earth. Thousands of aircraft every day move through a three-dimensional motorway in the sky. And it all depends on one thing: precise, real-time position data from space. Today, we decode the hidden satellite system that guides every flight. The core is the GPS constellation, 31 satellites orbiting Earth every 12 hours. Each satellite contains an atomic clock, a radio transmitter, and powerful solar panels. At any point on Earth, at least 4 satellites are visible in the sky. Those atomic clocks are so precise, they drift by only 1 second every 100,000 years. Your position is calculated by trilateration, timing how long signals take to reach you. Ground control stations constantly monitor the satellites, updating their exact position. The satellites broadcast radio waves that travel at the speed of light. By measuring the tiny travel time of the signal, the receiver calculates distance. The core formula is simple: distance equals speed of light multiplied by time delay. With 3 satellites, you get a rough position. With a 4th, you get altitude and clock correction. The 4th satellite synchronizes the receiver's less accurate clock with the atomic clocks in space. A dedicated antenna on the aircraft's roof captures these signals and feeds them to the avionics. Inside the avionics bay, the GNSS receiver processes signals from multiple satellite constellations. The data then flows to the flight management computer, the brain of the navigation system. The computer displays a moving map, showing the aircraft's position, waypoints, and route. It also integrates an inertial navigation system, which tracks motion without any external signals. If GPS is lost, the inertial system takes over seamlessly, using gyroscopes and accelerometers. Pilots can also manually select backup navigation sources from a panel overhead. Before departure, pilots load a flight plan made of 5-letter waypoints connected by airways. Over oceans, the organized track system changes daily to take advantage of wind and save fuel. Once airborne, the autopilot follows the programmed lateral path with incredible precision. The flight plan also includes a vertical profile, when to climb, cruise, and descend. On arrival, a published procedure guides the aircraft step-by-step to the runway. The result is a perfectly stabilized approach, even without seeing the ground. For approaches in poor weather, GPS alone isn't accurate enough. Ground stations help. A ground station knows its exact position and compares it with the GPS calculated position. It calculates a correction and broadcasts it via VHF radio to approaching aircraft. Satellite-based augmentation systems do the same, using geostationary satellites for continent-wide coverage. With corrections applied, the aircraft can fly approaches accurate to within a few meters. This allows safe landings in fog and low clouds, without needing expensive ground equipment. But sometimes, signals are lost. Interference, jamming, or satellite failures can happen. Jamming devices flood the frequency with noise, blocking GPS reception entirely. Pilots are trained to fall back on traditional navigation, charts, compass, and clocks. Ground-based VOR and DME beacons still provide reliable radio navigation worldwide, and the inertial system can maintain accurate position for hours, even without any external input. Redundancy is built into every layer of aviation, ensuring safety at all times. From a satellite in space to a smooth landing, navigation is a silent symphony. Source code daily is where we bring these hidden systems to light. If you value understanding how the invisible world works, please subscribe and turn on notifications. It really helps the channel. New deep dives into hidden systems are published every single week. Thanks for watching. Keep decoding the source code behind modern life.